We are all welcome to the 32nd Meteorological Virtual Seminar organized by Ghana Meteorological Agency, KNUST, and GCRF African Research. I'm your host, Ajaku Daniel, and today we'll be talking on cloudy days, techniques for nowcasting convective storms and solar radiation. And in the summary of this literature writing, we'll be looking at convective storms and how often linked to flooding and increasing frequency in the Sahel. And also it required improvements in nowcasting, especially where radar data is scarce. We first focus on nowcasting code pools, which is the CPs, and also look at the key features of convective storms measurable for the ground. Also, we are analyzing 10 years of time series data from the Northern Europe, and we'll apply this knowledge to measure the portable automatic weather station in Senegal, and also developing an AI-based tools to nowcast CPs in Dakar, which is the code pools. Additionally, we will discuss satellite-based nowcasting techniques for convective storm and shifts in the solar radiation nowcasting using geostationary satellite data to forecast surface radiation and also solar energy production. And this early morning, the person going to take us through this literature writing is Dr. Irene Livia Cruz. Dr. Cruz, please, you're welcome.
Hi, thank you, Daniel.
All right, so please, you can share your screen and we can start with the presentation.
Yes, let me try.
Okay, so please, as she's trying to share her screen, this is the format to which the presentation is going to go. So we are all going to wait for her to finish the presentation before we all ask our questions. So there will be no question midway. If you have a question, you jot it down. Then when she's done with the presentation, we'll open the chat box. You can also raise your hand and you ask the questions. Thank you very much. Dr. Livia, please, you can continue.
Thank you very much. Do you all see my screen?
Yes, please.
And do you hear me all right?
Yes.
Okay, perfect. Thank you, Daniel. And thank you everyone at Ghana Met for this invitation. It's an honor to be speaking to you. So as Daniel explained, I'll be talking about nowcasting, and specifically nowcasting storms and nowcasting solar radiation. There will be space after the talk for questions. So please ask about anything I talked about today. Okay, so I'm, as Daniel said, Irene, and I work at the Danish Meteorological Institute, which some of you might already know because I know you came and visited us recently. And I just finished my PhD, and my PhD was on convective storms. So the first part of the talk will be about that. And the second part will be about what I'm doing at the Danish Meteorological Institute, which is working with solar radiation. All right, so let's begin. So as I said, we'll talk about nowcasting and convective storms. Nowcasting means forecasting in the near term, so for the next few hours, rather than for the next days. We'll start with a project that I worked on in my PhD in Senegal. This was a photo I took last year when I went to Dakar with my colleagues to do a field campaign that I'll talk about. And as you can see, here's a convective storm. So I will just go through how the convective storm starts. When you have solar radiation that heats up the ground, this heats up the air. You probably know this already, but I'll just go through it very slowly. And the air then starts rising, and it contains moisture. And the moisture can condense and turn into a cloud. And the cloud can become more and more full of energy, say, and that becomes a convective storm. And when it starts raining, the rain can evaporate. And the evaporation of rain makes cold air that falls to the ground and spreads out as a density current. And that's the cold pool. There might be other ways to call this. I don't know if you also call it cold pool. In our institute here in Denmark, there's other terms like convective downdraft or gust front. So there's several terms. I just use cold pool. It's very simple. And the convective systems or the convective storms can also grow into larger systems, which you're very familiar with, the mesoscale convective systems. And that's when we reach dimensions of more than 100 kilometers in size. And with those, you also have enormous cold pools that can reach these sizes. So when we think of nowcasting a storm, a convective storm, or a mesoscale convective system, it's very handy that we have cold pools that form underneath them, right? Because we can measure them from the ground. So we don't need fancy radars, or we don't even need to look at satellite data when we have a cold pool, because all we need is a automatic weather station at the ground, and that will pick up on the decrease in temperature when a cold pool arrives. I hope that's clear until now. And we'll use this to think of a nowcasting algorithm for storms, okay? So first of all, we measured cold pools from this tower that you can see in the photo. This tower is in the Netherlands, in Cabau, and it's a 200-meter tower in height. And it has weather stations at several heights. So what we did was, every time there was a storm in the summer, over 10 years, we collected all the measurements of cold pools to see how they look like in a time series. And this is how they look like. On the top is the horizontal wind anomaly. So the increase in wind when there's a cold pool. And on the bottom is the temperature anomaly. So the decrease in temperature when there's a cold pool. And you can see that the increase in wind lasts for even 45 minutes. And the decrease in temperature can last for hours. Now, we also looked at the vertical velocity and the humidity anomaly. So on the top is the vertical velocity, and on the bottom is the humidity anomaly. And you can see that the vertical velocity also has a peak associated with the cold pool. And we also have very dry interior. So that's just a good thing to know. The edges of cold pools, just so you know, are also associated with new convection. So when you have a storm and it rains and you have a cold pool, on the edge of that cold pool, you can have new storms. So now we have an example of a mesoscale convective system. This is from the UKCEH Nowcasting portal, which you might be familiar with, because I know that Cornelia Klein, had a talk also to you guys and girls about this. And this specific event was on September 25th last year. And it's a mesoscale convective system. You can see it's larger than 200 kilometers, and it's passing over the country of Senegal. And we see it from the cloud top temperature from satellite. And this was after the storm. I was in Dakar, and it was flooded in several places. So often these big storms are associated with flooding. And you know this better than me. So I'll be asking you later if what I'm saying is correct for you. So one more thing to add is we had these automatic weather stations. Let's see if you can see this all right. On the left, we have a map of 2 locations in Senegal: Dakar, the capital city, on the left, and Pout, the little town about 50 kilometers to the east of Dakar. And we put these 2 weather stations in the 2 locations. It's very different weather stations, but we were just testing them to see how they work. But they're very small. You can just kind of walk around with it and then place it on a pole. And the important thing is that they would measure at 1 minute resolution, because when you have 1 minute temporal resolution, you can actually catch the cold pool. So let's go back to the mesoscale convective system that we saw from satellite data. We could actually measure the cold pool of this convective storm in the 2 locations, since we put the weather stations there. So you can already try to guess what you would measure in Pout and then in Dakar, right? You'll have a temperature drop, first in Pout and then in Dakar, if it's how we imagine. And that is exactly what we found. So in Pout, so to the east of Dakar, the red curve is the temperature measured from the automatic weather station. And you can see that it drops. And the wind speed, which is the gray line, picks up, yeah? And then we have rain. And interestingly, then in Dakar, you also have a temperature drop, but later. And this is about 30 minutes. I forgot the x-axis. You'll see next with the plot when it becomes with more variables. But the same happens in Dakar. The temperature drops several Kelvin or several degrees Celsius, drops 6 degrees Celsius in Dakar. The wind speed picks up, and then it starts raining. And if we look at the other variables, we have, let's see, in green, we have the humidity. So a dry interior. In purple, we have the pressure. The pressure goes up. And then I also had the soil moisture. Soil moisture goes up because it rains. And in Dakar, the same happens. We also have lightning strikes measured in Dakar before the event. Okay, moving on. We needed more examples because this was the end of my PhD. And I was just able to put those weather stations at the end of the rainy season last year. So to be able to make a nowcasting algorithm, I needed more measurements of cold pools in Senegal. So we set up a simulation, which you are also probably very familiar with. We used WRF, which is the weather research forecasting model, and we simulated a whole rainy season over Senegal, the one in 2019. We used a nesting approach, which simply means that in the red domain here, we had 1 kilometer horizontal resolution, and we fed it realistic boundary conditions. Okay, so we're essentially making a realistic simulation of a rainy season. And then what we can do is we can extract the time series from 2 locations of that simulation. So it's like creating synthetic station data. So we have here the location of Dakar again, and then to the east, we have Pout. And here you can see, for example, we take out the temperature simulation time series. Oh, I see there's something in the chat. Oh, okay. So there's the temperature time series from Pout and Dakar over the whole season. This is just to show what kind of data we can extract from the simulation. Now let's look at what does a cold pool look like in the simulation and if it respects what we would expect from our measurements. Here we have the cold pool. This is just the temperature at 2-meter height in the simulation over Senegal. And you can see it's cold, and it's just a cold pool from a storm that happened in the simulation. But it looks very much like the one that we had seen in satellite in September 2023. So here you can see that the cold pool is moving from the east to the west, probably with its convective system. And first it's measured in Pout. Here you can see the temperature drops in Pout, the wind picks up, and then it starts raining. And then afterwards, about 30 minutes later, the temperature drops in Dakar. The wind picks up and it starts raining. So you might already have noticed that there's a pattern. When you measure the cold pool in one place, then you'll measure it a bit later in another place. And that's the nowcasting. Here you can see the other variables. The pressure goes up, the humidity goes down, so dry interior, and it happens first in Pout and then in Dakar. Okay, so this, I'll go quickly through it without explaining too much, but we basically train an artificial intelligence algorithm, but it's not as complicated as it might seem. Imagine giving a lot of examples of cold pools time series to an algorithm and telling it, please learn what are the patterns that can be used to nowcast the cold pool in another location, okay? So we train an algorithm by giving it inputs, and these are just time series, and telling it the output, so it learns how to predict. And we specifically give it inputs from the Pout and Dakar locations of the simulation, and we tell it to predict the arrival of a cold pool in Dakar. And we do one more thing before just feeding data to the algorithm. We separate the different kinds of cold pools into 3 categories. We have propagating cold pools, which is the example that I showed you. So a cold pool that's measured first in Pout as a temperature drop, and then in Dakar. But in the simulation, we also have non-propagating cold pools. So cold pools that were measured in Pout, but they never made it to Dakar. And then we also have not cold pools, so just random time series. So it's good to feed the algorithm the different kinds of cold pools, so it learns all 3. And especially the middle one is important, because if we just looked at the time series by eye and we saw a cold pool in Pout, then we would expect a cold pool to be in Dakar, right? If we saw a temperature drop in Pout, we would think, there will be a temperature drop in Dakar 30 minutes later. But that's not always the case. And that's where the AI algorithm becomes interesting, because it can learn the patterns that make the cold pool get to Dakar or not. Okay, So here's an example of after training the algorithm, how does the prediction look? So here, for example, we're giving the input of temperature input. We're also giving other variables. But in the plot, I just put the temperature to make it more simple. So this is what the algorithm sees. It just sees that it's about 301 Kelvin input. In Dakar. And input, it's about 299 Kelvin, say. But then we see that input, it starts decreasing. So we might think a cold pool is on its way. And let's see what the algorithm tells us. This is the prediction. The prediction is the red crosses. And the labels, which is what actually happened, are the green dots. And you can see that, yes, the temperature indeed went down. It was a cold pool. And then in Dakar, the temperature went down. And it was predicted correctly with about a 30-minute lag. So it's a nowcast of 30 minutes. So that's a propagating cold pool. So let's see another example. We have these two time series from Put and Dakar, and we ask the algorithm, what is going to happen in Dakar? It tells us this is what it predicts. And in fact, it's not a cold pool. It's just a normal time series. And then last but not least, let's look at this example. Here, there's a very strong decrease in temperature in Put. So we would expect a cold pool in Dakar, right? But in this case, it was a non-propagating cold pool. And the algorithm was able to pick that up. So this is kind of cool. Okay, so the point of all of this is that we have a nowcasting algorithm that was trained with simulation data to nowcast cold pools in Dakar based on time series from Put and Dakar. And obviously, we would want to apply this to real-time measurements. And that's what we're waiting for in this rainy season, is to gather real observational measurements throughout the whole rainy season, and then retrain this machine learning algorithm with data from the weather stations for a whole season. But the cool thing is that you could technically do this in other places. You just need time series of rainy seasons. So I would imagine that you also have weather stations, a network, in fact. And if you have the temporal resolution that's high enough, so 1 minute temporal resolution, 1 minute temporal resolution, you could also make this kind of nowcasting algorithm in Ghana. So we can talk about this later if any of you are interested. And of course, we can also simulate similar thing like over Senegal to have even more data to train the algorithm with. Okay, now I'll move on to the second part of this talk. So the first part was on convective storms, and that was what I was working on in my PhD. But now that I'm finished with that, I have started my job at the Danish Meteorological Institute. And there I'm focusing on solar radiation nowcasting. And you might think, first it was the rain and the cold pools, and now it's the sun. Why am I working on that? Like, how does the second relate to the first? And actually, very similar, because it's all about where are the clouds. So now I'll go to Denmark in my talk, and then I'll try to connect to Ghana. So the whole question here is, we have the sun, we have solar radiation, we have solar panels, and we'd like to know how much energy can we make in the coming hours. For example, if there are going to be 2 hours of a lot of sun, then it's nice to know that we can, charge our phones, etc. But if a big cloud is going to come by, then we won't have solar radiation, we won't have solar energy, and we can't charge our phones. So knowing where that cloud goes is really important for nowcasting. And as you saw in the previous slide, we'll use satellite data for this. Okay, so we have a satellite data set, clouds and solar radiation. This is just a snapshot over Denmark from a few days ago, the 23rd, 2 days ago. And you can see here the surface solar radiation in watts per square meter. If it's dark, there's a cloud, essentially. And if it's orange, there's clear sky and a lot of solar radiation coming to the ground. And I can recommend looking at this website, MSGCPP, It was created by the Dutch Weather Service, KNMI, and they create this product, which is based on Meteosat second generation, so MSG, satellite retrievals, but it calculates the solar radiation at the surface. And it covers the whole domain of MSG, which means also Ghana is included in the domain. So I'll show you one more thing before going to the nowcasting. In Denmark, we also have a network of solar radiation ground stations. They're called pyranometers. Here's an image of the network. This was also from 2 days ago. It updates every 10 minutes. So for example, you can see over this little island here, it's clear sky. And in fact, the stations on the island were measuring a lot of radiation. Okay, so what we do to nowcast solar radiation, this is something I've been working on very recently, so it's very fresh, and please ask questions. But we basically take the satellite images from the last time steps. This is an example of the satellite images from MSG CPP at 1:15, at 1:30, 1:45, every 15 minutes. And we take those and then we apply an optical flow-based algorithm. Now that just means an algorithm that looks at where were the clouds and finds the velocity vectors of the clouds and then moves them forward in space based on their past movement. So these are the past time steps. And if we apply the optical flow-based algorithm, it can guess the future time steps. Here you can see it tells us, okay, in 15 minutes, the cloudscape will look like this. In 30 minutes, it'll look like this. 45 minutes, it will look like this. And you can see the whole scene is kind of moving to the right and a bit up. You can see that by the edge of the domain. And we're using here solar steps, which is an algorithm that is available online. It's on GitHub, for example. You can look into this paper by Alberto Carpentieri. It's a really nice paper. I can recommend reading it. Okay, so now that I've shown you the algorithm, how it works, but we can also just pick out one pixel from the image, say corresponding to where we have a solar radiation ground-based station, to then compare. So we're going to pick out some locations from the map, and we'll look at the time series of solar radiation from the past and predicted into the future. So here's again a map of Denmark. We have 4 locations that we chose. One is also on that little island I showed you before that's often sunny. And here on the bottom, we see the time series for each location from left to right. We have the 4 locations from left to right. In blue is what the ground-based stations are measuring in watts per square meter. In green is what we get from the satellite from the past, in the same locations, just extracting the pixel. You can see it follows quite well. It's not perfect, but it's okay. And then in orange and in gray, we see the forecasts, or the nowcasts, since it's in the near future. And we can see that, for example, in this second one, the forecasts are saying that the sun will pick up. So even though it's very, very cloudy, it's going to get less cloudy in the next hour or so. That's what the forecasts say. Small. And in orange, I put the solar steps forecast with that algorithm I showed you. But yeah, here you can see how we make the solar nowcasts. And the one on the right, you can see it's just a sunny day on the little island. Okay, so now to round off my talk, I think maybe I went a bit too fast. I'm sorry. But I'd like to show you what I tried to do for Ghana, and then we can discuss as much as you want. So I tried to apply the same algorithm to Ghana. And here you can see, for example, a satellite image from MSG CPP over the Ghana domain. And then I applied the same algorithm, solar steps and probabilistic advection, on the time steps from the satellite data preceding this image here to forecast for the future. And I did this for July 20th, so 5 days ago, and I'm outputting 2-hour solar nowcasts at 10:30 local time. And then since this is in the past, so it's actually a fake nowcast because we know how things went, I could also put on top of the forecasts or the nowcasts, I can put the actual satellite measurements so we can see if the nowcasts were good or not. And here's an example for Accra, Kumasi, and Tamale. And you can see that on this specific day, it was quite cloudy. So you had about 400 watts per square meter. That is about half of what you have on a clear sky day. And in Tamale, it was very cloudy. It was even 0 watts per square meter in these hours. So maybe in Kumasi, it was a day to get some solar radiation, but not in Tamale. And the interesting thing here would be if you had solar radiation measurements from the ground, like kind of the ones I showed you in Denmark, it could be nice to make a comparison to see if the satellite data matches the measurements from the ground. So then we could kind of use this algorithm with more confidence. So just to round off, I'd like to show you this same day in Denmark. So this was a fun exercise. So I looked at July 20th in Denmark, and here's how it is. You would never expect this. If you live in Denmark, you understand the joke, but it's usually very cloudy here, and it's almost never sunny. But on this particular day, it was actually very sunny in Denmark. As you can see, even the forecasts have almost no uncertainty because there were barely any clouds. So here you can see Ghana on that day, and here you can see Denmark on that day. But most of the time, it's very cloudy in Denmark, like in this image in Ghana. Okay, so now to round off, I'd like to tell you that you're very welcome to reach out for any questions, for any ideas, for any comments you might have. This is my email at the Danish Weather Institute. If you'd like to know more about cold pools and mesoscale convective systems, you can look at my thesis. This is my PhD thesis. The link here is on the bottom. And if you'd like to ask, for example, if that could be useful, then please reach out. Thank you.
All right, thank you very much, Dr. Cruz. We are really grateful for the insightful presentation that you made on the convective storms. All right, so we will open the floor for questions, but before that, if you have a question, you can actually go to the reaction aspect, raise your hand, we ask you the question, or you can type it in the chat box so that we read it out to Dr. Cruz. Then she makes it out an answer for everybody. All right, so before anybody asks, I have some few questions to ask to open the floor so that people also ask their questions. So the first one I have is you spoke about the wind speed and the temperature anomaly. So I wanted to know if there's a threshold or there's a specific range we would have to meet for the wind speed and the temperature anomaly to receive rainfall over a specific area.
If there's a threshold for
Yes,
the
please.
temperature anomaly and the wind
And
for the
the wind
cold
speed.
pools,
Yes, please.
yes, I can bring you also to the slide about the cold pools. Let's see. Okay. So just a quick question to you. When you see my screen now, do you see the whole slide or do you also see my Zoom?
Yeah, I see the whole slide.
Oh, perfect. Okay. So in general, to determine if it's a cold pool or not, there are thresholds, but these are not set in stone, let's say. In Northern Europe, for example, for this study here that I'm showing on the screen in the Netherlands, and you can look up the paper, it's called, I think, Cold Pools in the Netherlands, or you can just look up my name and the co-authors. We had a threshold of 1.5 Kelvin temperature drop in about 10 minutes or so to say this is a cold pool. But in the Sahel, I've seen that the cold pools can be much, much colder. So probably you could even make that threshold a bit larger to make sure that it's not just a sea breeze, for example. So maybe 2 Kelvin, something around that. And then having that drop in a short time, I would say then it's most probably a cold pool. There might be rain associated with it and wind speed increase associated with it.
All right, thank you. So moving on, there's a question in the chat box. Hayford is asking how accessible is the MSG CPP data?
How easily? Oh, yes. So let's see. It is accessible and it's very easy. I can maybe show you how to access it in live. Let's see. I had the link on the slide, so you can also try clicking it. 1 second.
Sure.
Here. Okay. So here, if we click on the link, let's see if it works for me. Okay. Do you see my screen?
Yes, you can see.
I'll make this big. Okay. So you can either go to the viewer and you'll get the latest image. And I've experienced it to be about 30-minute lag from the time the scan was done by the satellite. So from 15 to 30-minute lag. But you can see it in real time here, or you can download it directly to your laptop. And I can show you how to do that. But here you can see the viewer. You can choose the variable. The variable I was showing you was surface downwelling shortwave radiation. So here, if we zoom in on Ghana, you'll see it seems sunny. Am I right? It seems to be about, in the north of Ghana, about 700 watts per square meter. And in the south, maybe a bit more cloudy. We have, on this map at least, like 400 watts per square meter to 600. Does that correspond if you look out the window?
Sure. Yeah, sure.
Okay, cool.
All right, so there are still some few questions in the chat box.
Okay, well, yes, sorry, I just wanted to tell you that if you wanted to download it to your laptop, you can also look at the data access, and it explains to you how to, you can click on this link and it downloads the latest image.
All right, so
yeah.
So moving on to the question in the chat box.
Of course.
Christopher is saying, nice word.
Oh, hi, Chris.
He's wondering about what information satellite provides about cold pools, and also for nowcasting in those places where we don't have such great weather stations data.
Thank you for this really good question. So I have to point to another nowcasting portal, which Christopher might know much better than me, and which I think you also might have experienced using. So let's see, I have it in the back. Sorry, I will just, I'll share my screen again here. Do you see this nowcasting portal?
Yeah, you can see.
Okay, so this is the UKCEH nowcasting portal, which is also really nice to see satellite data in near real time. This is more for the looking at mesoscale convective systems. And Chris is asking if we can, or how we could look for cold pools from satellite data where we don't have 1-minute automatic weather stations. And I do this when I take a break at work. I like to look at this nowcasting portal and look for cold pools. And it is possible, especially in the visible radiation. So let's see if we can hunt for cold pools here together. What I tend to do is on this portal, which is accessible, you just look up nowcasting portal UKCEH and you find it. And it's updated quite frequently. I think this is from 9:30 local time. So about, an hour ago. Let's see, you can put, I'll just update it. Maybe it's even more recent now. Oh, 10:15. Okay, perfect. But we need a mesoscale convective system. Do we have any? Does anyone know which day in the past week had a mesoscale convective system around the Sahel? Then we can find it on the map.
All right, Dr. Cruz. So I was actually thinking maybe the data aspect, we can save that question for the last part so that we can have room, since there are many questions in the chat box. So we can probably save that for the last part. Then when we're about to close, we can delve into that and we will address that question. All right, so there's a question from,
I'll just tell Chris, if you can think of a day where there's a good mesoscale convective system, then I can show where one can see the outline of the cold pool, perhaps. And in the meantime, yes, Daniel, I'll answer other questions. Sounds
All right,
good.
sure. So, Camara is asking, are there mathematical calculations to determine the area covered by the cold pools?
The area covered by the cold pools.
Yeah, if there are any mathematical calculations to determine those areas.
That's a good question. So if you want to think about it mathematically, a cold pool can often be approximated with density current theory, if that is something you're familiar with. So a density current is essentially an area of dense liquid that moves in, or a volume of dense liquid that moves in a volume of less dense liquid. So imagine oil in water. And if you let that go, the dense liquid will move towards the less dense volume. And you have a current. So you could probably calculate, if you know how much denser, or how much it's raining and how much the temperature drop is, you could probably make a calculation of the volume of the dense air produced through evaporation. And that could maybe give you an idea of how large the cold pool will be. But I'm not an expert on the theory side, but that could be worth looking into. I hope that was kind of an answer to you.
I also hope you answer this question. So, Mr. Raphael is also asking, he wants to know if cold pools can be applied in localized rainfall or it's only meant for the mesoscale systems.
Can you repeat that? Sorry.
Right, so Rafa wanted to know if the cold pools are applied for localized rainfall or is it only applied for the mesoscale systems?
Oh, okay. I would say both localized rainfall and very extended mesoscale convective systems will have cold pools, as long as there's rain and the rain can evaporate. So the boundary layer is dry enough for the rain to evaporate. Then you have a cold pool. In Europe, for example, we have a lot of isolated convective systems. They're quite small. They pop up in the summer. So say from June to September here, you might have isolated convective systems, and they can be just maybe 2 kilometers in size. The rain cell, the cloud, the cumulonimbus cloud. And then the cold pool can be like 10 kilometers in size. And this is a tiny cold pool. But if it's a mesoscale convective system, then you'll have, instead of 2 kilometer convective cloud, you'll have 100 kilometer convective cloud, and you'll have perhaps a 200 kilometer sized cold pool. That's how I see it. It's just a matter of scaling.
Oh, okay, sure. All right, so a date has been provided by Mr. Ubakar, but once again, we will address that issue at the end. So we will just keep notes of the dates from 15 to 16 July for the convective activity, so we can use it for the data question. But as I said earlier on, we'll address it at the end part, so we can take questions when we are done. Then we address that aspect too. So Joyce is asking, how do you validate or verify the accuracy of the nowcasting predictions?
How do we validate?
Yes, please.
Yes, good question. So that's something I'm in the process of doing right now for the solar nowcasting. And to validate the nowcasts, I'm now comparing with the actual measurements. So a bit like I was showing, let's see if I can open this again. Like I was showing in the very end here, here was the example of the nowcasts and the actual satellite data. And even better, if you also have ground-based measurement, then you can make a comparison between the forecasts and the ground-based measurements and see how far off the forecast was from the ground-based measurements. And that's something I'm in the process of doing right now, because this work is very fresh. So, but here you can see if the actual measurement falls within the spread of the forecasts, and if the spread is not too big, then it's a pretty good forecast. So maybe here the best forecast is on the right in Tamale on this day. And the ones in Denmark on the 20th of July where it was sunny, they're just falling very close to the forecasts because there's no clouds, so not much uncertainty. Yeah.
All right, sure. So I realize most of the questions are moving towards the convective storms, but I have one on the solar radiation nowcasting. So let me shift it in so that we can balance the equation a little. All right,
Sounds
so
good.
you spoke about the solar radiation algorithm, and I wanted to know if the algorithm considers the wind direction and the pressures over an area before giving us an output for the forecast.
Okay, so for the solar nowcasts here, so you're asking if it also considers the wind, right?
Yeah,
Is that
considers the wind direction and that of the pressures over the areas.
okay? So in a way, yes, it considers the wind, but not directly. It doesn't look at the wind field. It just looks at how the clouds are moving, and that indirectly gives us the wind field, if you think about it. So the optical flow algorithm, it looks at the past movement of a cloud, for example, and then just moves it into the future with the same direction and speed. And then you can do that, but on many, many objects. So if you have many different clouds of different sizes, they will all move based on how they were moving previously. So you're not telling it what the wind is, but it's in a way picking up what the wind is from the images.
Oh, okay, sure. All right, so there are a few questions in the chat box, but I'll move back to the chat box and ask. So Raphael is also asking, for the analysis of the cold pool charts, as you've shown, can we confidently say that we can get rains when temperature increases with decreasing winds? But okay, let me try reframe. If I get it towards what you were talking about, it's supposed to be a temperature decrease, that is the anomaly, and an increase in winds. So he wants to ask if can we confidently say that if these conditions are met, we are actually receiving winds over the specific area?
That's also a very good question. I would say we need more measurements. I can't confidently say yes to this because I don't have enough measurements that I've seen myself where you see the cold pool and then rain. But all the measurements I've had so far from the Senegal campaign, I would say yes, we see a decrease in temperature, an increase in wind, and then rain. But we have to have more measurements to be confident in this. And it might also be that the cold pool arrives, but the rain goes somewhere not exactly over the point where you're measuring the cold pool. That can happen.
Oh, all right, sure. So from what he's rectified with me right now, he's trying to see that he understands the analogy you are giving with increase in winds and the temperature anomaly, but he wants to find out in the inverse what would happen.
In the
In the inverse format, what will happen?
Oh,
As
in
in
the
when
inverse.
temperature increases and winds decreases, what will happen?
Well, that's a good question. That I don't know. So the inverse of a cold pool, that I don't have an answer to that. I'm sorry. So if it becomes a bit warmer, you say, and if the winds
Are decreasing.
decrease. You got me there. I don't know.
All right, sure. So I think we'll probably probe into that, and next time, if he has further questions or maybe you have solutions to the problem, he's going to look up onto your email so that you give him an answer to that specific question. Thank you very much. All right, so Mr. Benja is also asking, what is the significance of cold pools with regards to cloud formation and rainfall performance?
Okay. So for me, the interesting thing about cold pools and cloud formation is something I mentioned in the very, very beginning of the talk, very briefly, which is that cold pools can trigger new convection. So when it rains and you have a cold pool, then on the edges of that cold pool, you might have new convective storms, or say clouds that turn into convective storms that then rain, right? So in a way, it organizes the cloud field because you'll have one storm, you'll have a storm maybe next to it or around it, and then that will make a new storm somewhere close by. So you have this upscale growth of a storm. while it's moving. I hope that isn't too complicated. I might have explained that in a bit of a complicated way, but essentially cold pools can lead to new convection. I think that's the main takeaway here. So if you can see where the cold pool is, and we'll get to how you can see that, thanks to Christopher's question, when we look at the data, then there's a chance that there will be a new storm on the edge of the cold pool.
All right, thank you. I'm sure maybe his question is also answered. So it's now from Ghana Meteorological Agency, so trying to ask a question. She wants to know how does nowcasting techniques for convective storms and solar radiation be applied effectively to improve weather dependent industries such as the agri sector.
For the agricultural sector?
Yes, please.
That's very interesting. That might even be a discussion we can have with each other, because I'm not familiar with the agricultural sector and what you need in the agricultural sector. I would expect that when choosing when to irrigate fields, for example, it would be good to know if it's going to rain in the next 2 hours, because if it's going to rain, then you wouldn't want to waste water by irrigating, right? Because it's going to rain anyway. So that could be a nice reason to have a nowcasting algorithm for all the fields, the country. And for the record, we also don't have that currently in Denmark. So we're also thinking, how can this be beneficial for the agricultural sector here? So that could be one thing, irrigation, knowing when to irrigate. And the solar radiation, I would need to talk to a person from the agricultural field, but I'm wondering if maybe there's a good time to sow the seeds, depending on when there's going to be a good amount of hours of sunlight. I don't know. That's something we could discuss. Someone knows better than me.
All right, sure. So we have an agro unit in our department. So after this, we'll have a basic discussion with them, and anything, we'll actually organize a meeting with you back again, and we'll know how to go about the whole thing. All right, so before I read out Kamara's question, I have one question. You spoke about the temporal resolution of 1 minute for the cold pool, but normally some satellites have a 15-minute temporal resolution. So those with a 15-minute temporal resolution can't detect the cold pool or what. So that is what I wanted to know.
Okay, it's also a good question. So the 1 minute resolution I find very important for time series data. So when you just have a point, so one little station, and you have a time series and you don't have spatial information, then it's very important that you can capture that very fast decrease in temperature and increase in wind. For satellite data, you actually have spatial information. And when you can see a cold pool, and we'll get to how, I can actually say it now, because then we'll look at it in the data portal. But sometimes from the visible radiation from satellite, you can actually see the edges of a cold pool, because you'll have clouds forming on the edges, like I mentioned. Then you can see a nice, say, we can call it a front around a mesoscale convective system. And then you can just see that snapshot, and you don't need higher temporal resolution to know there's a cold pool. And you can expect it to spread in space. And so the next image from satellite data will tell you how far has it gone. Does that make sense?
Yes, that makes sense. All right, so moving on to Kamara's question. He's trying to ask, what are the health implications of cold pools for, and how long will it last? The health impact of it and how long it will last. That is for the cold pools.
That is also a good question. I had never thought about this. I can't think of health impacts. Besides, I mean, the cold pool itself is just a bit cold for maybe an hour or so. But I think the largest health impact in this theme is when we're talking about convective storms. They often bring very strong rains in localized areas, right? And so that can lead to flooding. That's at least what I've seen that time in Senegal. When there was a massive scale convective system, parts of the capital city would get flooded. And I can see that being having health impacts that are not favorable if it was flooding. But the cold pool itself, I don't think is the problem, say. I hope that was a good answer. Maybe there's more to look into regarding health impacts of.
Right, sure. So Esther is also asking, are there any limitation or challenges in now casting convective storms and the solar radiation? If there's a limitation for the two, the now casting of convective storms and that of the solar radiation.
Yes. The answer from my side is yes, there's certainly limitations in nowcasting both convective storms and solar radiation. For me, the biggest limitation is the time window that you can nowcast in. So for example, for the cold pools, in this specific study that I showed you, we had two locations, right? We had Dakar and Pout, and they were 50 kilometers away from each other. And the storms tend to flow from east to west. And that 50-kilometer distance gives about a 30-minute lag between a cold pool measured in one place and a cold pool measured in the other. So the nowcasting window is there. We might get a bit more nowcasting potential. So maybe 45 minutes, maybe an hour if we had more distance between the stations or more stations, that could make the window a bit larger. So I would say that's my main limitation that I see in this algorithm, at least, for storms. And for solar radiation, you also lose a lot of information in the future because clouds, they evolve. They don't just move, right? They also become smaller or bigger or change pattern or disappear. And you can't really know what's going to happen in 2 hours or in 5 hours based on the last hour, right? You can just see how they're going to move for the next hour or so, or 2 hours, but I don't see that window being much longer just by satellite data. I hope that was clear.
I also hope the question was answered for Esther. All right, so someone is also asking, in terms of emergency response, what can we associate cold pools with? Do we say a cold pool can be associated with flood events, or we pay attention to temperature and wind changes prior to the passage of a cold pool or after the passage? All right, so if I'm to summarize it, I think he's trying to ask if the cold pool is associated with flooding events, or just its passage will bring a rainfall event.
Okay, thank you for the question. That's also really interesting regarding emergency response. So I can't say that every cold pool will be associated with a flood event. But I could say that if I were if I were back in Dakar and I wanted to know, is it going to rain? Then I would look at the time series from a station, for example, the one in Pout. And if I do see a decrease in temperature, an abrupt decrease in temperature, and an increase in wind, and I also look at the nowcasting portal and I see that there's a mesoscale convective system to the east of Senegal, then I could expect that to be soon hitting Dakar, right? That's kind of the concept here is if you see that the temperature is going to go down or is going down and the wind is going up, there might come some rain soon associated with the mesoscale convective system, if you can also see it in the satellite imagery. So I would say if you have high resolution weather station data and you do see this kind of pattern, it could be a advice or a slight warning that there might be some rain soon, depending on where the station is, of course, compared to you.
All right, thank you very much. So, Dixon is also asking, what are some challenges in accurately measuring the modeling of cold pools in our sub-region, that is Ghana?
Okay, thank you for that question as well. So the challenges in measuring cold pools, I would say, are having high enough temporal resolution from your weather stations. I think the standard temporal resolution for automatic weather stations is 10 minutes. And that's a bit too coarse to capture cold pools because the temperature goes down in less than a minute. But if you have 10-minute temporal resolution, you probably won't capture that. It will be kind of averaged out. So I would say that's the main challenge. And then you need real-time data. So if you have a weather station and all the data is being saved into, say, a little log, you need to go to the log to get the data, then it's too late, right? But if the data gets sent via the internet somewhere, then you can see it in real time. And having a weather station that's connected to the internet, I think, is not super easy. It was difficult for us to do it here. So maybe you have ideas on how to do it with your weather institute. And regarding modeling cold pools, that's also a really good question, because cold pools, the kind of the structures within a cold pool are actually quite high resolution. You need at least high resolution modeling to capture cold pool correctly in a simulation. And what is high resolution? That's debatable, but my simulations at 1 kilometer horizontal resolution, they were able to create fairly realistic cold pools. I've seen studies that go even to 500-meter resolution or 100-meter resolution to make them more and more realistic. But you don't need to do that. I've seen cold pools in 4-kilometer resolution simulations that they don't trigger new convection in a realistic manner because they're simply not strong enough with that resolution on the edges. And they're basically completely gone in 9-kilometer resolution simulations. So when we're looking at the IFS model, for example, I don't know if you use that as boundary conditions, you won't see cold pools usually, unless it's an enormous convective system.
Oh, all right, sure. So there are 2 questions in the chat box. We are going to take it so we can move on to the data aspect for the sake of time. But I would like to ask a question before we go on to the 2 questions in the chat box. All right,
Yes.
so you made mention of your colleague Cornelia, and we were actually working with her alongside on an NFLIX project, sorry. So
Cool.
with hers, we were actually looking at the brightness temperature and that of a core located over an area to give rise to over the area. So I wanted to know, with the projects we are doing with Cornelia, what is the difference between the cold pools and that of the convective, the core locations and the brightness temperature?
Okay, I need you to explain to me one more time what you're doing in that project, because I'm sorry, I didn't catch it completely.
All right, so in that project, we were dealing with convective storms too, but we are looking at that perspective from the core locations and that's of the brightness temperature. But
Yes.
you
Okay.
are taking it from the aspects of a cold pool, so I wanted to know the difference within all these.
Thank you. That's also a really good question. Okay, so and they are connected, and I think we could connect the 2 even more. So I know that Connie and Chris, they have this really nice algorithm that Connie wrote, where if you have infrared imagery, and that's probably also in the portal, if I open the portal again, here. If you have infrared imagery, that would be cloud top temperature. We still need a day with convection, and it's not quite loading. Perfect. Here's a pretty big convective system, right? And you see it in the infrared, meaning you see very cold cloud top temperatures. And then Cornelia has made this algorithm where you can actually see where are the cores, the convective cores. So that's, if you click here on convective cores, you'll see these outlines, which show you where are essentially the deepest part of the convective system that is often, or you could associate with where it's raining, most probably. Okay. That's how I've understood her research, which I find fantastic. And you can see they've also now superimposed the lightning data, which are these black pieces here. These are it's the new lightning data from Meteosat third generation satellite, which come out every 5 minutes. And where the lightning is, it's often also where the cloud is very deep, from my understanding. So you can see very nicely that the core corresponds to a place in the mesoscale convective system where there's also a lot of lightning. And then to connect it to my cold pools, I wouldn't say my cold pools, but to the cold pools I've been talking about, you could also expect that where it's raining is also where the cold pool is created, right? Because you need rain to evaporate. So I would expect that around here, you'll also have a cold pool, but that's something we would have to confirm. And that's also partly what the campaign in Senegal is going to try to confirm, because now there's a lot of weather stations in a network here to the east of Dakar, which you can actually also see in the portal if you go into observations here, Dakar East Station Network. But essentially, if this mesoscale convective system moves over Senegal, then we'll have a lot of little time series at the ground at 1 minute resolution to see if when the core passes over the network, we also measure the cold pool. And that would be what I expect. I hope that answers your question.
Yeah. Yes, please. Thank you very much. All right, so moving on to Johnson's question. Okay, so he's asking, now casting is useful within a short period of time. Sometimes it won't be 100% perfect. So what can be done to improve the perfectness? Let me just use the word effectiveness of the nowcasting.
That's a good question, Johnson. I wish you could answer that for me. Yeah, it is true that nowcasting is useful within a short period of time and that it won't work 100% perfectly. Both things very true. And what can be done to improve it? That's something we would have to all work together on. There's probably to improve, say, the trustworthiness of an algorithm. I would say you use several algorithms together, because then you can see if you have other methods to predict the same thing, and they're all the methods are saying it's going to rain, then you have more trust in the fact that it's going to rain instead of just trusting one method. So that would be my approach, is to just have a larger portfolio of nowcasting methods, whether it's for rain or for solar radiation or for, whatever you think is important. Then I would have just more than one method for the specific variable that you're trying to nowcast.
Oh, all right, sure. So this way is also asking that in nowcasting, we are more interested in the onset, intensity, and the cessation of the storm. So how good is the algorithm in predicting all these factors he has mentioned above? And also, is the algorithm statistical or is it a dynamic algorithm? And what are the variables involved with the algorithm?
Okay, thank you for the question. This is a complicated question. Let's see if I can answer. Okay, so you're interested in the onset, intensity, and cessation of the storms. That makes sense. And how good is the algorithm in predicting each of these? So you're asking about the cold pool nowcasting, right?
Yes, please.
Okay. So we are not able to nowcast the onset of the storms with this algorithm. For the onset, I would point more to Cornelia's work and Christopher's work at UKCEH about where to look for on a map of, say, land surface moisture anomalies to understand where storms might initiate on a given day. I don't know if you're familiar with these papers. I can send you links. But those are really good to think of where could a storm initiate. And that's not what we can do with the cold pool algorithm. Because for a cold pool algorithm, to be able to nowcast, you need to already have rain that is formed somewhere that is creating a cold pool, right? So the storm is already in its mature stage before we can use the algorithm to say it's going to rain. So unfortunately, this algorithm cannot nowcast the onset of the storm. But it can nowcast the onset of the rain, maybe, if that makes sense. I don't know if I understood onset correctly for you. I see onset as the initiation, but if you're interested in when it's going to rain where you're standing, then this cold pool nowcasting could be useful for that. The intensity, that's a good question. That could be a part of the algorithm if we put in more variables. So you asked what are the variables, and currently the variables in the cold pool nowcasting are temperature and wind, but also humidity and pressure, and I believe there was one more. And the wind in both directions, so across longitudes and across latitudes. If we also added precipitation in there as a variable in a smart way, we could probably also find a value of the intensity of the coming rain. That could be an interesting project. And the cessation of the storms. Sorry, were you saying?
I thought you were done answering the question, but if there's a continuation, you can go on.
It was just, I was thinking now of the cessation of the storms. So obviously we can't, with this algorithm, estimate when the storm is going to dissipate, but we could estimate when the rain is going to stop, because it's probably connected to how long it rained in the other location that you're using. So if it rained for 30 minutes there, you can expect that it's going to rain for 30 minutes here, I would think. So maybe that's something that the algorithm could learn also, besides the intensity. That's a very interesting question. Thank you.
All right, sure. So we are going to take the last question so we can move back to the data question, which is for 15th to 16th of July. So the last question is being asked by Benja. And he says, since cold pools create divergent flow away from precipitation areas, are there impacts on the aviation?
Okay, thank you. Also, very, very interesting question. So I'm not an expert on aviation, and I haven't spoken to anyone in the aviation sector. So don't take my words as the ground truth. But I do think there could be an impact on aviation on the edges of a cold pool, because the gust front on the edge is not only creating divergent flow away, but there's also convergence that brings air up. So there's also updrafts on the edges of a cold pool. And these updrafts can be several hundred meters up in the air. They can be measured several hundred meters up in the air, like I was showing you in one of the first slides from the measurements from that 200-meter weather tower. And I've seen radar imagery, for example, where you can see the edge of a cold pool, and you can see it even at 800 meters height. So I think that could create turbulence for aviation, or it could be an issue. But at the same time, I think that generally pilots do not fly close to mesoscale convective systems. So because they can see that from radar, right? So I would expect that a pilot either flies around a mesoscale convective system or over it, but not close to it. So maybe it's already by seeing that there's a mesoscale convective system, you already are aware of the risks of also its cold pool, if you know what I mean. But that could be very interesting to talk to someone in aviation about this, if they've noticed this from flying.
I think the concept you give really answers the question. So we are going to mute the questions for now, so we can address the convective data question. Then probably we'll end with the seminar. So please, there was a data slated for 15th to 16th. If we can use that date for the convective system, then probably see if we can get what we wanted. Yeah, 15th to 16th July.
Okay, let's look. So you're still seeing my screen, right?
Yeah.
Okay, and let's see. So just to understand, are you familiar with this platform, or would you like me to explain how I use it?
I'm sure we can just move ahead with this explanation.
Okay. So let's see. Here we're in the Sahel. We choose the 15th of July. Oh, that's a nice day. Okay. Thank you. Whoever suggested this, thank you. This is perfect. You can see there's a big mesoscale convective system here. Maybe if we go back in time. Oh, I lost it. Okay, here it is again. Okay, so what we're seeing right now is cloud top temperature in oranges and yellows, and the convective cores, thanks to Connie's algorithm. And we also have the lightning in black here. You can see there's a lot of lightning going on, right? So based on what we've looked at today, and the fact that a core is often associated with strong rain, you could expect that underneath this core, there's also a cold pool at the ground, right? So if you had little weather stations around here, you would probably be measuring a decrease in temperature. And then what Chris had asked earlier, which was really interesting, is how can we actually look for a cold pool if we don't have the weather stations at the ground? And there isn't a study on this, as far as I know, that shows these edges of cold pools in the Sahel. So this could be an interesting study to work on. But what I do in my spare time is I also open up here the visible radiation. And then let's see if I can change the map to another color. Here's the light map. So now the visible radiation is green. Very hard to see here. But sometimes, here could be an example, sometimes you see these lines of visible radiation around a convective system, especially close to the core. And these are, in my opinion, and I think is backed up in research regarding cold pools in other parts of the world. On the edge of a cold pool, there's shallow clouds being formed, and they can be seen in visible radiation. And in my opinion, we can see them in this portal as lines. So it would be a fun exercise if you're ever looking at this portal to look for these lines around a system. And let's see if we go forward in time, if it works. Sometimes it lags a bit. Let's see. This one should show up soon. Give me a second. We've lost the clouds. I'm sorry. Let's see if they show up. Okay, well, the clouds are gone. But my point was, if you look for these lines around a convective core and around a mesoscale convective system, you can sometimes see the edge of a cold pool. And that could be a way to guess where it is. Oh, here the clouds are back. It's just a matter of patience, I guess. And just to make you brainstorm with me, there's a very interesting, let's say, correlation that one can try to make, which is when you see this line, can you see a new storm forming on the line later on in time? And if you can see that happen, can you also correlate that with the ground, like the soil moisture anomaly? This is just to make a brainstorm start. And that's something I've been thinking about lately, because to initiate a new storm on the edge of a cold pool, you need the right conditions. It needs to be the right conditions to create new convection. It's not enough to just have the convergence. You also need the moisture. You also need the heat from the ground. So I have a theory that if it's very dry, then you have the right conditions, because it's going to be hot and you'll get the moisture from the rain, from the evaporation of the rain. And then you have the perfect conditions for creating a new storm. But this is going into another conversation. But here, if you look at the land surface temperature anomaly, which is here in between blue and brown, this light brown is dry or warm, and the blue is moist or cold in the morning of this day. And I would expect that if this core makes a nice cold pool line, which we can't see in this image, but then we might expect a storm to be forming somewhere around here over the dry soils. Anyway, I hope this answers the data question, which is essentially just look for lines in the visible radiation around convection for cold pools.
Yeah, sure. Thank you very much. All right, so with no further question, we would like to appreciate you for actually becoming to our call for the 32nd seminar series. We are really grateful you were able to log on to actually share insightful thoughts on convective storms and also solar radiation. Right, and we are also grateful to everybody that was able to join. So addressing the issue of how to get the video and the presentation slide that Dr. Cruz presented, those are registered. When the video is ready, we have a mailing platform that is going to send the output to everybody. So with this, we can say next time when the seminar link is given out, we should please kindly join, and we should please kindly also accept the invitation that is going to be sent by the organizers, so that in due time, when everything is done, we'll be able to share to people. So before we end, can we kindly turn on our cameras so we can capture everybody on board? Then we bring the seminar to a close.
It's nice to see everybody. Hello. Hopefully next time in person.
Yeah, sure. All right, thank you everybody for joining once again. We are grateful to have everybody on board. Please have a blissful day. Thank you very much.
Thank you so much.
Thank you.